In this lesson, we're going to continue naming ionic compounds and writing formulas of ionic compounds, but we are going to be doing this with transition metals. So the reason that the naming is a little bit different when you have a transition metal is because most transition metals, which are the metals we haven't talked about yet, the metals that are located in the D block. Most transition metals have multiple oxidation states. And that means that they can have more than one charge. Oxidation is the loss of electrons. So the oxidation states show the number of electrons which have been removed from an element. So part of the standard is you need to be able to explain the rationale as to why elements have multiple oxidation states. So one of the examples we're going to look at is for iron. So the reason that something like iron would have multiple oxidation states is because the 4s and 3d orbitals are very similar in energy. So electrons can be easily lost from either orbital. So looking at a picture of our relative energy levels, if we're looking at the 4s orbital and the 3d orbital, they are very similar in energy. Energy increases up along the y-axis. So since these orbitals are so similar in energy level, that means that we can easily lose electrons from either orbital. So let's look at the electron configuration for an iron atom. Using our noble gas notation, it would be argon, 4s2, 3d6. So iron can lose 2 electrons from the 4th energy level. And if it loses 2 electrons from the 4th energy level, its electron configuration would now be argon 3d6. Since it lost 2 electrons, it would have a charge of 2+. Well, that 3d orbital is very similar in energy, so iron can also lose an electron from that 3d orbital. And it would be argon 3d5. If orbitals are half full or completely full, that is more stable. So a d orbital could hold up to 10 electrons. If it is half filled, that is a more stable configuration. So iron can also lose another electron, and then its electron configuration would be argon 3d5. But the important thing to know is that the reason that an atom like iron can lose electrons in an S4s orbital and a 3d orbital, the reason that it can form multiple oxidation states is because those orbitals are very similar in energy level. There are a few exceptions to know. So typically when we're talking about elements with multiple oxidation states, we're talking about elements in the D block. Tin and lead are in the P block, but they have multiple oxidation states. So make sure you're aware of those. Tin and lead have multiple oxidation states, even though they're in the P block. Zinc is in the D block, but zinc will always be 2+. Zinc is an element that does not have multiple oxidation states, so this is one you should memorize. Zinc will always be 2+. Cadmium will always be 2+. Silver will always be 1+. So those are 3 that you should know. All right, so now getting to naming and formulas. We'll start with formulas. A few of these rules I'm not going to write down because we've written them down in the last 2 sets of notes. Anytime you write an ionic formula, the cation comes first, followed by the anion. We need to determine the ratio of ions needed to make a neutral compound. Ionic compounds are always neutral, so we need to make sure we have the correct ratio. When you're looking at the names, you're going to notice that there is a Roman numeral. So we need to know what that is. The Roman numeral indicates the charge of the cation. And then one thing that we haven't mentioned yet, because typically I don't see students do this until we get to this lesson, ionic compounds, the ratio should always be in the most reduced form. So the ratio needs to be reduced. So let's say you wrote a formula of Pb2O4. Both of these subscripts are divisible by 2, so we would want to reduce it down to PbO2. Okay, so let's look at some examples. Write the formula for iron 3 sulfide Let's do lead 4 oxide. Manganese 2 nitrate. And let's do one more. Let's do iron 2 sulfate. So we said that the Roman numeral indicates the charge of the cation. So if this is iron 3 sulfide, iron would have a charge of 3+. We could look up sulfur on the periodic table. Sulfur is going to have a charge of 2-. The cation always comes first. The anion comes second. And now we need to think of what ratio is needed to make a neutral compound. And we would get Fe2, S3. If I have 2 irons, that gives me a charge of 6+. If I have 3 sulfide ions, that gives me a charge of 6-, so my net charge is going to be 0. B, lead 4 oxide. Roman numeral is the charge of the cation. Oxide is oxygen. Oxygen is 2-. We need to cancel out this +4. Oxygen is only -2. So I would need 2 oxygens. 2 oxygens, each with a charge of -2, is like a -4. That's going to cancel out that +4. Manganese 2 nitrate. Roman numeral is the charge of the cation. Nitrate is a polyatomic ion. NO3-. We need to think about the ratio of ions needed to make a neutral compound. If manganese is 2+, but nitrate is only -1, I'm going to need 2 nitrates. And then remember from last lesson, anytime you need more than 1 polyatomic ion, it has to go in parentheses. If not, it looks like I have 32 oxygens. So I'm going to put nitrate, NO3, in parentheses, and since I need 2 of them, that's going to go on the outside. Last one, iron 2 sulfate. So the Roman numeral tells us the charge of the cation. Sulfate is also polyatomic, and it is SO4 2-. Iron is +2, sulfate is -2. This is going to be a 1-to-1 ratio. So my ionic formula would be FeSO4. So the reason that we need the Roman numeral is if not, we don't know what the charge of the cation is going to be. If this just said iron sulfide and iron sulfate, we would have no way to know or indicate whether it's going to be +2 or +3. So the Roman numeral tells us the charge since these elements can have multiple charges. Let's go to naming. So again, cation comes first, anion comes second. Never change the name of the cation. But we are going to add a Roman numeral in parentheses to indicate the charge of the cation. So again, we have to add that Roman numeral in so we know what the charge of the cation will be. For the anion, we are going to follow the normal rules that we already use. If it is just an element on the periodic table, drop the ending, add IDE. If it's a polyatomic ion, we're just going to write the name of the polyatomic ion. So these ones are probably the most difficult because you have to do an extra step. We need to add a Roman numeral to indicate the charge of the cation. So you need to figure out the charge of the cation. So if you don't know the charge of the cation, start with the anion. Well, sulfate has a charge of -2. Ionic compounds are neutral, so the net charge has to equal 0. If sulfate is -2, that means copper would have to be +2. I have 1 copper and 1 sulfate. It is a 1-to-1 ratio. If sulfate is -2, that means copper has to be +2. So this would be copper to sulfate. We could look up SO4 on our polyatomic ion reference sheet. It is sulfate. Never change the name of a polyatomic ion. B. Again, we don't know the charge of the cation, so start with the anion. Oxygen is always -2. This is a 1-to-1 ratio. I have 1 iron and 1 oxygen. If oxygen is -2, iron has to be +2 to get to a net charge of 0. Cation comes first. Never change the name of the cation. Add the Roman numeral in parentheses. Follow the normal naming rules for oxygen. We are going to drop the ending of oxygen and add I-D-E. C. We don't know the charge of nickel, but I can look up the charge of nitrate. This is polyatomic. It is made up of many atoms. Nitrate always has a charge of -1. But be careful because now we don't have a 1-to-1 ratio of cations to anions. I have 2 nitrate ions. If I have 2 nitrate ions, each with a charge of -1, we can think of that like a -2. So nickel would have to be +2 in order to cancel that charge out. So this would be nickel to nitrate. So again, you have to remember that there are 2 nitrates. If I have 2 nitrate ions and they each have a charge of -1, we could think of that like a -2. I know my net charge has to equal 0, so therefore nickel has to be +2. Last one. Sulfur has a charge of -2, and there's 2 of them. So think of that like a -4. Cation would have to be +4 to cancel that out. Sn is tin. We're going to add the charge of the cation using Roman numerals in parentheses. S is sulfur. We're going to drop the ending of sulfur and add I-D-E. SnS2 would be tin for sulfide.